to classrooms bigger than this one with 60 or 80 students, so I'm used to talk without the microphone. So I would like just to, first of all, thank the director and the institutes, the Physics Institute of the University of São Paulo, to host this event, this workshop. They are being very helpful, and then all the infrastructure, and I would like to ask the Marcos Martins, the director of the Institute, to say a few words, and then I will make the general remarks. Thank you, Marcos.
Thank you, Mauro. Good morning, everybody. I'm here just to welcome you and say that we are being helpful, but we are very happy to have all of you here. It's a very nice opportunity for you to know the Institute of Physics, and also for us to have some students to know better the Geant4. So it's a very nice opportunity, and we are very glad to have you all here. So I know that you have a lot of work ahead, so I won't take more time of you. Okay, thank you, Mauro.
Thanks, Marcos. So just to end up with the thank you session, so I would also have, it's my duty to thank FAPESP for funding this event. And of course, more importantly, I would like to thank Makoto Asai to promptly accepting, and Dennis Wright and Mihaly Novak. They are the lecturers, so you'll be very used to hear and read their names. And I would like also, just before we start, to end my participation, just saying a little bit of the motivation of this course. So during my PhD and my postdoc time, I was always stumbling on people saying, look, this is made by Geant4. This is made by Geant. You should understand this. And then we never understood this. We just take what was needed to get the job going, right? So you do just the needed things to get the work going on, and without having any idea of what was really going on. And I feel like most of the students will, at some time, face the same issue. So I was also discussing with Marcelo for a long time that he also sees the problem here in the university. So at some point we decided that we would like to have a class or something that we would try to organize ourselves. We would try to teach ourselves. But then at some point we realized that it would be possible to bring the real thing here. So these guys are the real thing, and we are very thankful for you coming here. And let's start. So I think that the first lecture is Dennis. So thank you, Dennis. Maybe yes, the other one.
It's already connected up to here.
Okay.
You can just start.
Yeah, okay. No, I don't. Well, before that comes up, let me just say, on behalf of Makoto and Mihaly and myself, I'm very happy to be here. We're all very happy to be here, and for the three of us, it's the first time in Brazil, so we're looking forward to discovering a little bit of your country. Also, it's an honor for us to be here because not only is it the first Geant4 tutorial in Brazil, It's also the first one in South America, so we're breaking ground here. And it's just starting to come up.
We're going to try this, want to use this.
That would be good, yes. So far, I don't see it coming up on the screen now.
Maybe we need to... But you have to label.
There's a USB here. Okay, it has.
Your keyboard cannot be identified.
Just
okay.
close it. You can just just close it. That's okay. I think for the screen you need not to mirror it. You cannot mirror the.
Yeah.
If you go to this symbol.
No. Then just click the full screen mode.
It's in full screen.
No, it's not.
Oh, now it's out. Yes, so view, full screen. It's not getting my...
I think if you...
I take it. Stop it. And
Yeah.
Actually, it recognizes yours.
I don't think it recognizes the screen. Oh, there it goes.
Yeah, it has two screens.
Yes. So,
No.
somehow it's small, but it works.
So if you want to move lines
Okay.
and the laser in the middle.
Right, thanks. Okay, now we're finally online. To begin with, we'll talk about something which doesn't directly pertain to Geant4, but is more general, and that is on what is Geant4 based. So it is basically a Monte Carlo simulation code. And we'll just talk about what Monte Carlo is and then how Geant4 uses it. These are some slides that Makoto developed some while ago, and I condensed them and also added a little bit of explanation going along the way. So we'll start with a review of Monte Carlo methods, and then talk about the basics. So probability density function, mean, variance, and standard deviation. I'm sure you know all about this, but within the context of Monte Carlo simulation, it may be a little different. And then how do we apply these to Monte Carlo or simulation problems? So two of the basic problems that we do all the time, for example, would be decay and flight, and Compton scattering, amongst many other complicated physical processes. And then we'll talk about how to boost the simulation. So this is called the variance reduction technique, and a lot of times you'll want to speed up your simulation in some way, and Monte Carlo is the way you do that. And then just a partial list of the Monte Carlo codes that exist out there for solving problems. So it's essentially a method of numerical analysis, and it uses random sampling to somehow reproduce what's going on in the real world. Lots of applications. So, particle physics certainly, quantum field theory, astrophysics, we could just keep going on and on and on. There are some more real-world calculations, simulating traffic flow, for example, also uses lots of Monte Carlo, and environmental sciences and stock market simulations also use Monte Carlo. So let's start with the very basics. The Monte Carlo method is a stochastic method for numerical integration. In the end, you may have the most complicated detector in the world, and you want to find out some signal. So what you're really doing is a complicated integral. And we can let the computer do most of the work. And so we go back to statistics to look at some of the basic things. We just assume now that we have n random points. So these could be considered to be some kind of data point, for example. And we want to say, when you distribute these points, what is the score of these points? How important are they? And what do they mean for your detector? So going back to the basic statistics, then we have these things called the mean, which you know, and the mean of the square. So this is just the sum of the data points, and then the sum of the square of the data points averaged over the number of points. Now we rely on the good old central limit theorem, which is stated here, so that as the number of trials or the number of random points that you sample gets larger and larger and larger, supposedly you get closer to reality. And that comes by, first of all, looking at the standard deviation. So this is the mean of the squares of the data points minus the square of the mean divided by the number of trials, minus 1. And as you can see, it fits in this probability distribution. And so as n gets very large, sigma squared gets very small, and this distribution becomes very sharp. So very much focused, supposedly, on the thing that you are trying to simulate. So let's go back to 1777, and probably the first use of geometrical probability, called Buffon's needle. And so this is a very nice little experiment that you can do is take a big piece of paper or draw some straight lines on the floor, equally spaced, and then have a number of sticks or needles with the same length and just throw them on the floor. Count the number of times that a stick or needle crosses the lines that you've drawn on the floor, and from that you can calculate pi. Okay? So that's a very interesting calculation to do, but the basis of it is here. So let's suppose these are the lines that you draw. Distance between the lines is capital D. And here is the needle in red. And so they all have the same length. And it will fall at some random angle. And then you just count the number of times that it crosses either this line or that line. And you can come up with the probability, which is 2 times the length of the needle divided by pi times the distance between the lines. So that's a very basic and understandable way to calculate pi. Now we go to 1886, and Laplace calculates the area of pi by using a distribution of random points over a square. So you take a square, which is a unit on 2 on each side, so 2 by 2, and throw points uniformly in x and y, and then count the number of points that fall inside the circle divided by the total number of points that you try. And you get, as you increase the number of points, you get a number very close to pi, and it's something like this. So those are all nice and easy, and now we start to get more difficult. So going forward to 1930, Enrico Fermi develops a random method to calculate the properties of the neutron. And then the Manhattan Project in the 1940s, does simulations using for the development of thermonuclear weapons, and von Neumann and Ulam coined the term Monte Carlo. So we owe them the name that we use. And now in 1948, Metropolis developed the first actual computer code. And as soon as you have computers, you need programming languages. So now in 1963 was the first time that you're actually doing something that resembles what we have in Geant4 today. So we have coupled electron-photon transport, and that became ETRAN, and then from ETRAN evolved a whole lot of other programming languages. And since then, it's just many, many different simulation programs have been developed, and we'll talk about a few of those as we go along. So the basics. The most important thing, or the first thing to look at, is the probability distribution function. So if we have a random variable, we can also call it a stochastic variable. It means its value cannot be specified in advance. So we can only observe it. We can't predict it. And so if x is some continuous random variable over an interval, that interval can be finite or infinite, but we just pick something randomly in this interval. Now we know that the value can't be specified in advance, but we can make some statements about the probability that it will be above a certain value or below a certain value. And so for that, we have something called the probability distribution function. So it's a function of a stochastic variable, and it has these three properties. You have to define it on some interval. So it could be finite ends or it could be infinite ends, but A and B must be specified. It cannot be negative, so non-negative in that interval. And you have to be able to normalize this function. So let's call it f, integrate it over that interval. It always has to be 1. So the probability distribution function f is a density function. So if you have some random variable x which has units of energy, then the probability distribution function has to have units of 1 over energy. This is always a good way to check if you're doing these integrals yourself, because just doing the unit definitions can help you out and make things a little clearer. So for a given x, f, we're not yet at the probability, okay? This is distributing the probability over some interval. And x can have infinitely many values. And if you look at the probability of a specific value, it's infinitely narrow, so it's 0. Probability of any particular value is 0. So what we really want to look at, and this is the thing we start to observe, is this increment of probability. So the probability distribution times some interval dx. And now we do the random sampling and sample over some region between x and x plus dx. And this is just the probability function. So the f of x is the probability that this sample, every time you throw the dice, is between some region x and x plus delta x. And so here is the formal definition of the integral. Now we're talking about cumulative distribution function. So we talked about probability distribution function previously, and now we're going to integrate that to get the cumulative distribution function. So that's capital F of x. It's just the integral over this range from the beginning of the range to some value x of the probability distribution function. This has some properties, okay? F at A, at the initial point of the interval, has to be 0, and at the final point of the interval has to be 1. And because we know that the probability distribution function x, or f of x, is always non-negative, then we know that f of x, capital F of x, is always monotonically increasing. So CDF, cumulative distribution function, is a measure of probability. So now we have something we can use with the computer. So it's just the probability that that random sample of the variable will assume a value between a and x. Let's take some nice, easy examples, and suppose that we have a probability distribution function, which is this box between 15 and 25 in the value of x. And so the probability distribution function is then 0 up to 15, and then it is this 1 over b minus a in this region, and then back down to 0 at 25. And so the integral is just this simple thing, and you get x minus a over b minus a. So now, at 15, you have this linearly rising piece, which corresponds to the flat part, and then flat again at higher values. So just a nice, simple linear integral. Something more useful, now let's suppose we're talking about a radioactive decay, or some decay of a particle. Now we can look at the probability distribution function of that decay, which is an exponential. So the PDF, f of x, is this thing called, alpha e to the minus alpha x, where this could be 1 over time. Alpha could be have units of 1 over time. And so to find out what the probability of decay is, you could just integrate that to get the cumulative distribution function from start time 0 to some indefinite time x. and you come up with the function 1 minus e to the minus alpha x. And now this starts to look very familiar to exponential decay. So we have some isotope which is decaying with this probability distribution function, and the probability that it actually decays at some time t, or in this case x, is this function here. So up to now, everything has been quite easy. We can find a distribution function which has a nice functional form. We can integrate that without too much trouble. We know how to do the integral. Everything's great. But most of the time, things are not so nice. So usually we're going to have some messy function like that. So what can we do? We can draw a box around it and say, all right, we know that the function is going to be between here and here over this interval. So let's say we were interested between this point, and the function goes in this way. And so we say, let's then just, over this integral, let's throw a value of a random value between 0 and this maximum value. If that value is below the integral, then we keep it and count it. If it is above, we discard it. And then we take the ratio of those that fall under divided by the total number of tries, and that's just like Laplace's method for calculating pi in a box. So that's easy, and that is the sort of the intuitive way to do it. We can be smart by taking a better function. So there could be some strange function in which it has a maximum and it's very sharply declining, and so doing this would be very inefficient. And so we might want some kind of envelope function that allows us to be smarter about how we throw the random numbers. But for now, we'll just say this is the basics of it. So we throw a random number, and then we accept it based on whether it falls below the function or above the function. And that way we can do the integral or do the Monte Carlo. So we go now back to the formal definitions, and this is all statistics, and so I'm sure it's quite familiar to all of you, but let me just mention what the variables are. So we will be dealing with, of course, the probability distribution function f, and this function has a mean and a variance. So the mean, of course, is the expectation value mu is just the weighted integral of the probability distribution function over some integral. And then the standard deviation measures the spread of this random variable. So a large standard deviation means it's going over a large range. And that's also very easy to calculate from statistics. That was the variable itself, but you can make the same arguments about functions of that variable. So let's say that z is a function of a random variable, and it is also, the variable is described by the probability distribution function. Then you can calculate what the expectation value of z is with this integral. So here is the function z that you want to simulate, and here again is the probability distribution function. So just do the integral of the product over that, and you can get the expectation value. And once again, you can do the same thing for the variance of z by getting the standard deviation. So this is what Monte Carlo is all about. So we're talking about the variance, and we are trying to calculate both the expectation value and the variance. And hopefully, if we're efficient and we know what we're doing in the Monte Carlo, we keep the variance small. It's called variance reduction. And eventually, if we're doing a good job and we take lots of trials, then the more samples we get, in the limit as n goes to infinity, we will approach the expectation value of this function. And that's what we want to try and find. Once we've done all that, and we've done our simulation, and we've taken our samples, we have to find out how much we believe that. Okay, we're doing random things. It's not clear that it's always going to be, for a particular number of samples, that it's always going to be the right answer. And we have something called a confidence level. So the confidence level tells us to what degree we are certain that we have approached the expectation value of that function. And you've probably all seen this before as well. So the probability that our expectation value is between the mean and some interval of the mean is given by this integral. Okay? And you can usually find a table to tell you what the confidence is based on the units of standard deviation. So if you're looking at a function and you want to say, what is the probability, what is the confidence, how confident are you that your answer falls between 1 and plus or minus 1 standard deviation of the mean, then you look down here in the column to lambda equals 1, and you see this expected number. So 68% is our confidence level that it's going to be between plus and minus 1 standard deviation of the mean, and so on and so forth. So you have to calculate three things. You have to calculate mean, expectation value, and confidence level whenever you do Monte Carlo in order to have a good understanding of what you've done. So some real-world examples. Let's look back to this decay in flight. So we have a decaying particle, unstable lifetime, and it'll decay in, let's say, a lifetime of t. And it's traveling with momentum p and therefore a velocity v. So the distance here is given. And you can write down the probability distribution function, as I mentioned in an earlier slide, as the exponential of minus t over r. And r here is the mean life of the particle. So the function is going to look like that. The next step of the function then is to calculate, or the next step of the Monte Carlo job is to calculate the cumulative distribution function. So we integrate this function over the interval minus infinity to t, and that will be equal to r. Okay, that's the mean life of the particle. Now, in order to sample where on this curve, so remember, once we integrate that curve, we have something that goes up like this. And we have to find out where on that curve that the decay happened. And so we set the value of the cumulative distribution function to some random variable between 0 and 1. And then we solve. So in this case, r is between 0 and 1. That's our random variable. And then we can say, the time of decay is minus the lifetime tau times the log of 1 minus r. So in this case, we can do the integral, invert it based on the random variable that we're throwing, and then calculate the lifetime. Let's talk a little bit more about some decays in flight. So this happens a lot in the Geant4 simulations, of course. We're going to have to find out where do pions decay, and how often do they decay, and where the final state particles are distributed. And so Geant4, in this case, provides you the correct branching ratio. So we know that a pi plus goes to a mu plus and a neutrino 99.99% of the time. And then there are some other decay branches which are smaller, but those are all included. And so the first thing Geant4 does is throw a random variable and says, well, most of the time it's going to be here, but sometimes you're going to get some of these rare decay branches. And they're all there. So that's the first job. That's done. We know now which of these is going to happen. And now we have to shoot some more random number generators because we have this pion, and it's going to decay into maybe 2 or 3 particles. But let's just look at 2. So let's look at this decay branch. It'll go into a muon and a neutrino back to back at some angle. So now we have to simulate what is the angle at which these particles will be emitted. And so this is just the phase space. So we know what the solid angle is going to be, sine theta, d theta, d phi. And we throw random numbers on the interval 0 to pi for theta and 0 to 2 pi for phi, and then do some calculations to find out what those are. So let me go to the next slide just to clarify a particular issue. One mistake that it's easy to do if you're writing your own Monte Carlo code is to say, well, I know I have to sample theta between 0 and pi, so maybe I should do this. Maybe I should just take my random number, multiply it by pi, and that's my theta. Intuitively, that seems okay, except when you do that, you're going to get this kind of distribution with these weird concentrations at the poles. And so, of course, you know that that's wrong because we're not supposed to be throwing it random in pi, but random in cosine theta. And so in this case, we throw the random number generated, then we invert it to find out what the theta is. We take the arc cosine, and we get the theta that way. The phi, for example, is going to be another random number generator too, and that's going to be a straight multiplication by 2 pi. And so for that, we get a non-biased uniform distribution on the sphere, and now we know where those particles are going after the decay. Now we can keep getting more and more real, and we can apply it to something that actually happens in physics. So we have Compton scattering. So the electron and gamma are scattering off of each other. So we have a gamma coming in, and it hits an atomic electron, perhaps, scatters at some angle, and then the electron recoils. So there, of course, is a formula for this, and there's a cross-section depending on the material. And we can write that all down. So the first thing we need to do is come up with the probability that it's going to happen given a certain amount of material in your detector. So this gamma is traveling through the detector. It has to go through many layers, perhaps. And you come up with something called a mean free path. Okay? And that allows you then to calculate your probability distribution for the location of this interaction to happen. So remember the cross-section for volume. You need the number of atoms times the cross-section for the atom. And that gives you eta. And now that you have eta, you know that it's going to interact with this function, exponential minus eta L, which is the thing you're going to sample. And that's the probability distribution function that we've seen before. So it's a nice, simple exponential. Now we do the same thing. We just integrate that over the length to find the cumulative distribution function, set the cumulative distribution function equal to your random variable, x, and then invert it. Or I'm sorry, r is the random variable. Invert it, and now you can calculate L. And now you know where in your detector this interaction happened. So now it gets more complicated. If we have a detector made up of lots of layers of different materials and different lengths, then this mean free path is going to be a combination of the length and the lambda, which is a function of the energy and the density. And so you will be able to do this integral. And the important thing is that the distance measured by the unit of mean free path is independent of the material. Lambda and L are, of course, material dependent, but this thing, n, is not. And so that's very useful as we go on and do complicated detector compositions. So what do we have? Let's suppose we have several materials that the electron goes through, and the probability distribution function is, as before, a function of n lambda, so that's exponential minus n lambda. And then we solve that and invert it. And so that says that for a given lambda, you're going to find this unit of mean free path. Now, let's suppose that it has gone through that unit of mean free path without interacting. Said, okay, but now we've gone to a different material. We have to adjust the mean free path for the fact that we have passed through this first layer. So we just subtract that off. We subtract off that probability because we've still got some left, and the particle has not decayed. So if that happens, then we have a new n lambda, and we keep doing that subtraction until the Compton scattering happens. Final step. So now we talk about the angular distribution of the Compton scattering. We know how often it's going to happen. We know where it's going to happen. And now we have to say, where are the final particles going to go in space? So we, of course, have a formula for it, and the formula is quite messy. And so here is a case where we have to use the acceptance-rejection method that I mentioned several slides ago. So we have some messy function that we can plot. It's hard or impossible to integrate. We have to use numerical methods, and this is perfect for Monte Carlo. And the whole key of Monte Carlo codes, and especially of Geant4, is to find an efficient way of doing that. So Geant4 does that for you, and it does this complicated sampling. So that's the basics of the Monte Carlo, but there will be many times in which the thing that you're looking for is rare. And so you'll run hours and hours of CPU, and you may not get a very good answer because the number of events is small, and so your statistics will be quite poor. However, you can help that by boosting it or biasing your Monte Carlo, and that's really the advantage of using the Monte Carlo method. You can speed things up a lot if you're careful. So let's go back to Buffon's needle once again. So now let's say we were not very smart when we were drawing our lines, and they were so far apart, and our needles were so short that the needle almost never crosses a line. So we need to throw a lot of events before we can actually get any that cross the line. You can see the problem. So if that's the situation we're in, then we can do this trick. So remember, pi was given by this function, so it was twice the length of the needle divided by the distance between the lines, times the number of crosses or hits divided by the number of trials. So that's how we calculated pi before, and as n got very big, then we could get a good value of pi. But this could be small if we've not done our experiment design properly. So what we can do then is bias that. We can multiply this by a factor d over 2L so that this becomes 1. And now we've boosted our simulation quite a bit. And we don't need to throw things quite nearly as often, and the same thing applies to any other Monte Carlo problem. So that's called variance reduction. And there are many, many clever ways to do variance reduction in Monte Carlo. As I mentioned, if you have a complicated integral, one of the ways to help that out is to find a good envelope for throwing your random numbers. But otherwise, this is a method which allows you to do things which might otherwise be impossible. So it's a very good thing. It's called variance reduction, and another way to put it would be to call it non-analog Monte Carlo. So that's just another name. And sometimes it's not always obvious how you're going to improve things. It's sometimes viewed as an art form to do the biasing properly. But we'll talk more about that in a couple days. So some use cases. One of the big ones, and probably one of the early ones, is efficiency of radiation shielding. So you have a radioactive source and you want to put some shielding around it. How thick should it be? What should it be made of? That's a good example. Response of a thin detector. It could be that your detector is microns thick and you're sending a lot of beams in, but because the thing is so thin, the interactions are very few. So you need to bias that in order to do it in a reasonable amount of time. Dose. So if you're looking at radioactive dose and you're trying to find out how much radiation damage is happening on an integrated circuit, for example. In that case, you are looking for radiation coming from the whole sky. And obviously, if you do that in Monte Carlo, you have a lot of rays that are coming in, and very few of them actually touch your very small detector. And so you might have to bias the distribution on the sky in order to get something which is done efficiently. And we'll talk about that too. So here is what is available out there, and it's only a small subset, but I talk about probably the more prominent ones. In electromagnetic physics, of course, there was this E-trend that I mentioned on the second slide for electrons and gammas. EGS4 was used a lot and still is in some cases for electron gamma transport. EGS5, EGS NRC, I believe, is the current maintained version. And Penelope is also a very good code for doing electromagnetic simulation. Now, hadronic physics is a little more complicated, and I'll talk a lot about that in the next few days. But for that, we have Fluka, Geant4, Mars, MCMPX, FITS. All of these do hadronics. These other codes also do electromagnetic, but these codes especially spend a lot of time, doing hadronic physics interactions. That's it. Are there questions? Okay, of course, anytime that you see me not here talking or during the hands-on or any other time in the hallway, please ask questions.
Where am I? Please. How can I turn this off? Okay, anyway. Okay, good morning. My name is Makoto Asai from Slack. And so before I start my presentation, I just make sure that you have already installed the Geant4 on your laptop. Okay? If you haven't, do it during the tutorials because download itself takes hours maybe, depending upon the bandwidth. And also installation takes another hours, depending upon your CPU. So if you haven't yet done so, do it now, okay? During the sessions, you don't have to look at it. You know, just let your computer do it. And if you go back to the main page of this Indico, you'll see the instructions. Okay. Okay. Otherwise, we start. Where am I? Where's my mouse? Okay, it is. Okay, perfect. Okay, so this is the introductory talk of Geant4, and okay. Oh, now it works. Please. Yes. Please is important always. Okay, so it contains the general introduction and brief history of Geant4, followed by we are now in Geant4 version 10 series since 5 years. So I'll introduce you of what's new in version 10 series. And of course, if you are new to Geant4 at all, you never saw older version of Geant4, so you don't care. But anyway, then I'll briefly show you the highlights of the user applications, so all the user domains, starting from high energy physics down to Homeland I should not say down, to the Homeland Security. So then just a few words about our license. Then I really start the tutorial here. The very basic of Geant4. So Geant4 is a general purpose Monte Carlo simulation toolkit for elementary particles and ions as well, passing through and interacting with matter. Okay? We started for the use case of high energy physics, but immediately it finds the another use cases in space and medicine, medical applications, now material science, or Homeland Security, or industrial applications, so on and so forth. And actually, there are a lot of job openings that require Geant4 nowadays, so learning Geant4 at even the undergrad students makes a lot of sense nowadays. And we offered most, if not all, of the functionalities that is required for the simulation. Okay? That includes, of course, the kernel, geometry, navigation, all the physics processes you may need, and scoring options, and GUI and visualization drivers. And thanks to the polymorphism mechanism of C++, if you have better physics than we offer, you can plug it in as you like without interfering to anything else. You can just plug it in, and it works. Okay? If you have nice, very nasty, complicated solid, the shape of the solid you want to simulate, you can plug it in. It works without touching to any other part of the code. That's a good thing. Okay? And we offer a lot of user guides and examples as well. And first of all, the geometry. Geant4 has by far the richest collection of shapes compared to any other simulation code that Dennis introduced you in his talk. Okay? We have constructed solid geometry like box or tube or poly, whatever, or Boolean operation, tessellated solid, so on and so forth. And as I said, you can extend it. And also, to describe your geometry, you can create a hierarchy like here's the mother volume, here's the daughter, here's the granddaughter inside, and so on and so forth. Or flat geometry, that is, put everything in everywhere in the world. And CAD system, CAD system always use this flat structure, but we can deal with it. And you can describe up to billions of shapes, as you like Atlas detector, which has, I don't know how many, but quite many. And also, we have some tools to check the complex structures, and also some interfaces to CAD system is available. And one of the biggest advantages of Geant4 in terms of geometry is we optimize your geometry so that the navigation or transportation of the particles in your geometry is fully optimized. Okay? That was not the case for any other simulation tool, including previous version of Geant3. And also, we can deal with motion. For high energy physics, you may not want to care about it, but for some other top use cases, in particular for medicine, you do need this motion. Okay? That is also very unique to Geant4. And physics, we have electromagnetic physics, hadronic physics, photon or lepton hadron processes, optical photon processes. So you can really simulate the optical photons reflecting in a light guide, if you like. And decay, of course, and sharp parameterization, event biasing options, and so on and so forth. And again, you can plug in whatever you like, if you need. And also, please note that for many cases, we provide alternative physics models so that you can freely choose what you need. Okay? For example, some physics models are more accurate as a cost of the computing power. Okay? So if the accuracy is the most important thing for you, you have to pick the most accurate physics options we offer, but it's slow. Of course, we have to calculate a lot. But if you want to roughly estimate what's going on, you always have option to pick whatever the simplified physics models that is well faster than the others. But it's up to you. Okay? The ultimate responsibility of choosing the right physics option is on you, not on me. Okay? That is a key. And also that is a bit of the difficulty of using Geant4, because for other simulation tool like Furuka, it's a black box. You don't know what you are doing, but it gives you something. Okay? So it's a totally different concept. So we started discussions of creating a new simulation tool called Geant4 in early 1990s when the super collider in Texas was slashed. So we lost what we are doing. So we started to think about what else we can do. So we started. Okay? So I'm one of the very beginning, so I'm dealing with Geant4 for almost 30 years. Okay. And so officially saying 94, the project started. And in 4 years, we made the first public release. And since then, it's already, already 20 years. And we keep updating and upgrading Geant4 since ever. And so several major architecture revisions has already been made. And first of all, in the very old days, there's no STL library, so we use something else. But when STL library becomes common, we migrated to STL, and so on and so forth. And the most recent big change was multi-threading. Because nowadays, I'll discuss it later, but all CPU come with more cores, right? More than one core. So there's no reason we should not use it. Okay, so multi-threading. So the latest version of Geant4 is 10.5. That was released at the end of last year. Please don't take this number 4 as a version. Geant4 is our product name. Okay, it's not Geant version 4. Okay, and we typically make one public release a year. So, in version 10 series, it was released end of 2013. The biggest thing was multi-threading. Okay? It took 5 years for us to make Geant4 fully multi-threaded with all the thread safety complications here or there. Geant4 has more than 2 million lines of code without any comment inside, inline commenting. So we really have to go through all the lines to check if there's any potential, race conditions. So it took 5 years for us to make ourselves confident to make the release. So anyway, and we also found with our surprise that even if you stick onto the sequential mode, Geant4 10 series is much faster than previous version, because when we worked for multi-threading, we cleaned up memory allocations here or there. That makes our code much cleaned up, and so it becomes faster. So even if you use sequential mode rather than multi-threading mode, you can always advise to use the latest version because it's faster anyway. Okay. For example, Atlas gain just 10-20% for free. 20% of all the simulation budget they use, it's a huge money. Okay. And also, the trend is now many core, many threads. So we've been testing with the latest Intel Xeon Phi coprocessors. Quite unfortunately, Intel announced they stopped developing it. But at least with Xeon Phi, we have already observed quite a nice boost. And fully multi-threaded, we can use not only the physical core, but even the fourth order hyper-threading, we gain some. Okay. And we are working with Intel, actually, developers, and they are quite pleased to see this curve. It's really a nice curve here. And also, not this past Christmas break, but the other, we try to employ an entire mirror supercomputer at Argonne that has 3 million threads. So we run Geant4 in parallel of 3 million threads. 3 million is a huge number, Once for time of just simulating one event, this generates 3 million events. So it's something. And the simulation itself is okay, but we also realize, even in a smaller scale, that is a smaller scale test. If number of threads is small, it's perfect. But if it's not the case, efficiency is not that good. Not because of Geant4, but I/O. For example, root is the biggest obstacle. So we really have to find a way to really, efficiently read and write the simulation input and data. That is basically outside of Geant4, but Geant4 cannot live without any output, So that is something we really have to think about. So what we do for multithreading is the following. The upper half is without multithreading. So you can still run Geant4 application for each core of your machine independently, or each thread of your machine independently. In that case, each core or each thread, if you like, requires this amount of memory, red and green. Red represents geometry descriptions and also cross-section tables, all the materials kind of things. Okay? And green part is transient part. That is track, heat, output kind of histograms kind of things. So each core or each thread, you need both of them. But in multi-threaded mode, we make Geant4 so that such that this detector geometry cross-section, they are common, are actually shared in memory. Okay? So that for each thread, only additional memory you need is transient part, tracks, heat. Of course, this has to be independent each other. Okay? So with this way, as you see, the memory you need is much smaller. In that is a key thing that nowadays, number of core or number of threads you have is just increasing a lot, while the memory space you have is not that. So we are now going back to the good old 1950s, let's say, where the memory is so limited. So we have to go this way. Otherwise, we couldn't do up to 240 threads running in parallel. Okay, so this is something I go back, I come back later, so let me skip it, please. Yes. So if you already have a Geant4 code running in sequential mode, or it run in older version of Geant4, it's not hard to migrate to version 10 series in multi-threaded mode. The only thing you have to make sure is your code is thread safe. Of course, that is the most difficult part. But if your simulation code is not ultra complex, it wouldn't take more than a few days to migrate. Let's say. Okay, how many of you, raise your hand if you have been using Geant4 before 10 series, so 9 series or older. Okay, thank you. By the way, who are very new to Geant4 at all? Just a few. Okay. Thank you. Now, the solid. In 10 series, we have more shapes and also new implementations. And in particular, optionally, we have new unified solid library. That is also called VecGeom. And that offers some cleaned up of the implementation of the logic of the shapes. And so, also, tessellated solid that I'm going to describe in my geometry talk has a big boost. So if you have complicated shapes, you are definitely advised to use the new solid libraries. For example, this is just one solid of a tracking sector, or tracking detector of LHCb at CERN. It has more than 1 million facets, but it's only one solid. And in the past, we say do it just for demonstration purposes. But now it's fast enough, so that LHCb is now quite happy. As you see, that the boost we got was 3 orders, so more than 1,000 times faster than before. So now you can really use tessellated solid quite efficiently. Now, in the physics, we have a lot of new physics still coming, or improvement coming. And Dennis and Mihaly will introduce you of all the new physics. Okay, and here or there. And for medical people, we now have DNA options, physics options, or I don't know if it's physics or chemical. Anyway, both. Anyway, so it really simulates not only the radiation itself, but all the radicals, OH minus or H plus is okay, protein, but OH minus or whatever, floating around, okay, in water. A new hadronic physics that Dennis should describe. Okay, and a new biasing scheme. And since 10.0, we are improving quite a lot about the event biasing options. This part was really a part we are falling behind quite a bit from MCNP, so we are now catching up. And new visualization tools. The latest version with Qt is really nice GUI. So we had a collaboration of a bit more than 100, scattering over the world. We have a few collaborators, I believe, in South America. I don't know which country it was. Maybe Argentina, Brazil. At one guy from Pico.
Oh, he's from Colombia.
Colombia, okay. Anyway. And so at least note that not only high energy physics laboratories, but space or some medical institutions as well. So now collaboration is made of quite a wide variety of scientists joining together. Please, okay. So for example, our first general paper, which was published 2003, so 16 years ago, has this number of citations. It's a huge number. And actually, we realized that this paper is the largest, has the largest citation CERN ever publicized. So is the case of SLAC. So it's something. And so the number is still growing rapidly. They do physics, astrophysics, medicine, engineering, energy, understandable. Mathematics, I don't know what they are doing. And biochemical, that thing is good, yes. Then economics, I have no idea what they are doing with us, no idea. But there are a wide variety of use cases. And this is the latest general publication. So if you use Geant4, please refer at least two papers, this one and that one, okay? And this one describes how we made Geant4 10 series. So how we made Geant4 free multi-threaded kind of things. All the details of how, if you want to learn how we modified our big code base to multi-thread, it's written here. And we are quite pleased to say that this is the most downloaded. And we could finally beat ourselves. This was a top download for 15 years. But now we beat ourselves, okay? Okay, so I'll briefly show you the highlight slides of all the use cases. And I hope you find at least one or two slides that is familiar to you, okay? So we always start with Babar, because Babar is the first pioneer experiment in high energy physics that started in use of Geant4. We started at year 2000. And so this is cottage of Dennis. And we started 2000 and with more than 20 sites in North America and Europe to simulate. Now at CERN, all the too large and too medium and too small experiment at LHC, all of them are using Geant4 now. This is for the case of Atlas. The innermost pixel detectors are aligned in the order of an accuracy of microns, while the actual size is more than 40 meters. So we definitely they definitely need to describe their geometry in double precision, you know. And Geant4 has already been successfully employed by detector designing phase, calibration alignment phase, and analysis phase. Okay? For example, alignment. They discover Atlas detector was mislocated for 1 millimeter because they carefully analyzed the data and the simulation, and they discovered just 1 millimeter shift of the simulation. Of course, they cannot move Atlas anymore. It's too huge. So they changed all the geometry for 1 millimeter shift. I don't remember which way. But now, all the missing ETs has a complete agreement. You know, missing ET is one of the most difficult things to simulate. Everything has to be right. Okay? Not only the physics, but also the geometry has to be exactly right. And so on and so forth. And they also use the carbon background study by Geant4. And actually, in space, this is exactly the first use case of Geant4 in space. And the mission is XMM, X-ray mirror mission. And the Chandra was NASA's satellite, basically the same thing, same apparatus, and was launched in 1999, early 1999. And their CCD camera that burnt out in a week. So ESA needed to study what's wrong in Chandra because they are going to launch XMM, basically the same thing, in 8 months later. So they simulated Chandra and understood what's wrong. Here's Chandra mirrors to focus X-rays. But when Chandra went through the radiation belt, protons focused. Slow protons focused to CCD, and it burnt the CCD camera. So ESA put beam shutter here. So XMM is still alive after 20 years. So since then, ESA is a big supporter of Geant4. Please. And a lot of other astrophysics experiments like glass Fermi, and all different missions. Some are already launched, some are already crashed, but some are still in the design phase. They all use Geant4 in one way or the other. Okay. For example, this radiation monitor went to the Mars, and it was actually designed by Geant4. And in international space stations, please. This is simulation of radiation. Of course, the irradiation of the astronaut is a big concern, but also another big concern is single event upset in a space. Actually, they have to reboot computers twice a day because of single event upset. So they really simulate how much of radiation dose they have with a serious geometry implementations. Here, Planet Cosmics is the largest it's an application built on top of Geant4. It has a magnetosphere and atmosphere of not only the Earth, but also Mercury, Venus, Mars, Jupiter, Saturn. So in this case, green lines are of course, a magnetosphere of the Earth. And this is actually one particle, proton, trapped in the magnetic field. This is even larger scale simulation. Someone simulate the solar flare with Geant4. It was actually the electron boost in the solar flare, because Geant4 can deal with motions. So they do it, and surprisingly, the agreement was very good with measurements. Now the completely opposite, smaller, one with smaller scale. this is the collaboration of Vanderbilt University, NASA Marshall, and SLAC, and Florida maybe. And we simulated semiconductor device. TCAD is a semiconductor simulator connecting with Geant4, and also SPICE. SPICE is a circuit simulator to simulate single event upset. Okay. Like this, we simulate energy deposition along the interactions, and then transport electron holes. And those are the data, actual data of the single event upset observed at the messenger mission, I believe, to the Mercury. And pink is our simulation. And this blue line is a previous older version of the simulation using the linear energy transfer. So that NASA has been using for decades. They realize their simulation is not good at all, but our simulation is better. And we can also do the activation. Okay. Now in medicine, Geant4 is already used by beam therapy, blood therapy, imaging, and irradiation study. All these use cases. And one of the key things of Geant4 is we can deal with motion. This is a so-called multi-leaf collimators. So if conventional gamma ray treatment, but if treatment heads rotate over the patient, this multi-leaf collimator, this guy, changes its size dynamically to shield the X-rays, not going to the healthy tissues. Okay, so they really have to simulate motions, quite important. Okay, and also, first of all, patient him or herself is moving. Okay, so they really need to simulate the motion. Okay, that is also quite important. So some cases we really can simulate even the single cell or DNA. We have DNA options that you can really simulate single or double strand blockage by radiation of the DNA. Okay, like this. We have already shown it. Please. Now, in one of the new area is phonon. This is not typo. It's a phonon sound. Okay, and propagating in a cryogenic temperature to 20-30 millikelvin germanium crystal for dark matter study. So, in addition to the electron hole drifting, these blue dots are phonon produced, so we can really simulate phonon now. So here, this is electron. Red is hole. Electron cannot go along the electric field because of the band structure. It's 40 degrees apart. But blue are the phonons, like this. Here's electron, and here's hole, and red, this time red are the phonon. It's almost like a shock wave. And also, bent crystal channeling. If you have a crystal structure, each particle travel along the crystal. It's trapped in the well of the potential. That is called channeling. So if you have a bent crystal, if particle comes from here, it's trapped in the bent structure. So actually, you can use it as a beam guide to extract the beam. And the simulation really fits well with this data. Okay. Now, LSST, this large synoptic survey telescope, it goes to somewhere in South America, right? Chile, okay. Anyway, so you may wonder why this conventional optical, telescope needs Geant4. Yeah, we're surprised they use Geant4. What they did was they simulate vacuum vessel, and they simulate atoms floating in a vacuum vessel and bumping on the walls to optimize where the vacuum pump should be. Okay, they really use Geant4 in that way. We could never expect this kind of use case. They modified optical photon processes, the reflection, and use bouncing. So, interesting. And this is another use case. It's a disaster. And this is Fukushima reactor. In this case, Los Alamos designed the muon tomography using the cosmic muons to do the tomograph, and they use Geant4 to optimize their detector. And here's one of the first data actually, and here's the reactor. Inside is empty. It's not good sign at all. But anyway, so Geant4 is used to optimize the reactors. And there are a lot of studies, also the soil or whatever. And now hottest topic here is Homeland Security. People need to inspect what's inside the cargoes. So this is something familiar to you, right? At every airport we have now these kind of things. But also this one, this shoots X-ray beams from this side, and here's the detector, and the truck goes through it. Or actually, maybe this is stopped. I don't know. Otherwise, driver will be radiated. I don't know which is which. Anyway, so they do simulations and optimize the apparatus using Geant4. Okay. So now a lot of security companies now hiring Geant4 experts. Yes. Okay. Any question up to now? Yes. Mm-hmm.
You said that there's a special part where you can consult the geometry and the cross-section and so on. So you share this space for all of it?
Yes, and I come back this my multi-threading talk for detail.
Okay. Because my question is, how is it done when you have moving parts? Because this is not the lookup table.
Very good question, and I'll discuss it in my geometry talk that deal with motions. Okay, thanks. But you have to remind me. Okay, license. Yeah, Geant4 license is shortest I've ever seen in any simulation code compared to MCNP, Fluka, eggs, whatever. It has only 8 points. The first 3, it says who we are, we made it, not you, and so on. Then it says you can use it as you like. And even if you download it, bake it in a CD or DVD or whatever, and you can sell it, you can make money if you like. It's okay. So, and you can modify and redistribute as you like, please. The only requirement you do is when you do this, you just say you use Geant4. It's not something you invented. Okay, please. And if you freely distribute some improvement, we have a right to pick it if we like. Okay, that is only requirement. And of course, the famous disclaimers. We don't guarantee it works. We are not guilty if it doesn't. Okay. Otherwise, if patient dies by missimulation, we don't want to go to jail. So disclaimers. That's it. So, as you see, download Geant4. It's open source. You can read everything. And if you like, you modify it and redistribute if you like, under your name. Go ahead. But please, you have to say you inherit Geant4. Okay? That's it. Okay, now real lecture starts for another 10, 15 minutes, I think. So, there are some terminologies, or you may call them jargons. Okay? So, the run is a unit of Geant4 simulation. It's an analogy of the real high-energy physics experiment. Okay, a run of Geant4 starts with your command, your order of beam on. So beam is on, so that you'll get data. Okay, sorry for medical or space users, there's no such beam, but anyway, this is our word. Okay, and within a run, you cannot change the detector setup. You cannot change setting of physics, okay? Because the experimental area is inaccessible. Conceptually, run is a collection of events which share the same detector and physics conditions. Okay? A run consists of one event loop. Even if you do multi-threaded mode, it's one event loop shared by all the threads. Okay? At the beginning of run, we optimize your geometry, okay, for the navigation, and we calculate cross sections, so that you may realize when you issued beam on, Geant4 may not start event loop immediately because we optimize your geometry. We're calculating cross sections. Okay, it takes some small amount of time. Okay. G4 Run Manager is a class that process run, and run itself is represented by G4 Run class, okay, or user-defined class derived from G4 Run. And a run class may have a summary results of a run, okay. And G4 user run action is an optional user hook. So if you want to do something at the beginning or at the end of the run, this is a class you have to implement. For example, you may want to define histograms, right? Now, event. Event is a basic unit of simulating Geant4. Simulation in Geant4. At the beginning of processing one event, primary track or primary tracks, more than one, are generated. Okay? These primary tracks are pushed into a stack. Each track is popped up individually from the stack and tracked. Tracked means Geant4 will take care of transportation or interaction, whatever. And once this particular track is done, there may be secondaries. So all these secondaries are pushed back to the stack again and popped one by one later. Okay? We do this way. So this tracking lasts as long as the stack has a track. Okay? And once track becomes empty, one event is over, so that we are free to move to the next event. Okay. G4 event class represents an event. Actually, this is one of the class you have to be familiarized because you get all the outputs of each event. Okay. So it has, of course, as an input, primary vortices and particles. And as an output, it has hits and trajectory. Okay? G4 Event Manager is a class that processes one event, and G4 User Event Action is a user's hook. So if you want to do something per event, this is the place you implement something. Now, track. Track is a snapshot of a particle. Okay? It's physical quantity of current instance only. Okay, that means, suppose here's a track. It knows, of course, where it is. It knows its momentum. Of course, it knows its proton or whatever the particle type. Okay, but it does not remember where it used to be. Okay, it knows only the current information. Okay, and we have step. It's a delta information that is applied to a track. So if a track takes a step, it moves from here to there. Okay? Maybe with different momentum or whatever. Okay? So step is applied. Delta information that is applied to a track. Okay? Once it is applied, track comes to this new point. Then track no longer remembers where it used to be. It only has a new position, a new momentum. Okay? So track is updated by step. Okay? And track object is deleted when it goes out of the world, so it will never come back. Or it disappears by decay, for example, or inelastic scattering, or absorbed. Or it goes down to zero kinetic energy and nothing else to do. Okay? And for example, you may decide to kill it. If it goes into the shielding block, you don't care. Then you may kill it. Okay? Please note, no track object persists at the end of event. When particle comes to its end, it's deleted from the memory. No longer remembered by any means. Okay? Time to time, you need to remember its trajectory, how it passes through. In this case, we have another class that is called trajectory. The trajectory and track is different object. We deal with track to do the physics, while for the recording purposes, we have trajectory. Okay? G4 tracking manager manages the process of a track. A track itself is represented by G4 track class. Okay? User tracking action is a user hook. Or if you want to do something for each track at the beginning or at the end, this is a place. You may now realize if you are geek of the object orientation, there's a design choice we made 20-some years ago. There's a discussion if track itself has all the methods to move itself by itself, or we have track object and tracking manager that split the functionality. We chose the second. Track is a container that remembers only all the physics quantities we need, while all the methodologies of dealing with track is in the different class of tracking manager. Okay, that is our design choice. Now step. As I said in my previous slide, step is a delta information that is applied to a track to renew the track information. Okay. It has information of the energy loss on that particular step, for example, the time of flight spent by that step, and so on and so forth. Also, it knows the volume and material of each point, start point and end point. Okay? And I'll discuss it later again, but anyway, please note, Geant4 always limit the step when a particle comes to the volume boundary. Okay? There is no Geant4 step moving from volume A to volume B. Okay? We always limit the step here. So when step is limited by the volume boundary, it physically stands on the boundary, but logically belongs to the next volume. That means, so that we know what is the next volume, we definitely need to know it for example, for optical processes. We need to know what is another material to calculate the reflection. Okay? But you have to know that the endpoint may logically belong to the next volume. That is important when you want to score the energy deposition, for example. You have to know, you have to always look up to the pre-step point that has the correct material of the step belongs to. Okay? Now again, the stepping manager and G4 step is a class that has the data, and the stepping action is a user hook. Now trajectory. As I said before, track does not persist. Okay? Track does not know where it used to be. Instead, we have G4 trajectory class that copied some of the useful information from G4 track and store it. And also, trajectory point is a class that copied some information from G4 step. For example, trajectory point remembered its position. Okay? So trajectory has a vector of trajectory point, of course. At the end of the processing, G4 event has a collection of the vector of G4 trajectory object. If you say tracking store trajectory to be 1, okay? because of memory consumptions, by default it is 0. We don't record any trajectory because you can easily imagine if how many tracks we have in a shower. It's huge. Okay. So please keep in mind the distinction okay, track and trajectory, step and trajectory point. So default trajectory point object persists until the end of the event, so that it's your responsibility to make sure you don't store too much. Okay? If you keep all the step, all the trajectory point, all the trajectory of the high energy shower, it easily eats up your memory, and you realize Geant4 to be very, very, very slow, because it's not fault of Geant4, but it's really, swapping disk memory. Okay. And because of the same reason, G4 trajectory and trajectory point store only the very minimal information. If you need more, you can extend it, but you have to be careful with memory consumption. Okay. Now, particle. A particle in Geant4 is represented by 3 layers of the classes. The topmost is a track that knows position and geometrical information. Okay? This is a class that's representing a track, a particle to be tracked. The middle layer is what we call dynamic particle. It has all the physics properties of the particle, such as momentum, energy, spin. So there must be exact one-to-one correlation between track and dynamic particle. Okay? So this class it represents an individual particle, but not vice versa. Means there are some dynamic particle objects that are not associated with track, such as quark. In some physics classes, they need to deal with quark, but for sure you will not see quark in your detector. So that's the reason we have 2 different classes. And the bottom class is particle definition. This has the static properties of particles, such as charge, mass, lifetime, and decay table. Obviously, if you have 2 pions, they have different positions. That means they need different 2 track objects. They have 2 different momentums. So they need individual dynamic particle object. But they both are pion, same mass, okay, same lifetime, same decay channel. So they are shared. Okay. So we need 3 different class objects. Got it? So tracking and physics, this is something Dennis will discuss a lot later. So let me skip. The only note I have to make here, although Dennis will repeat, is we have cuts, so-called production threshold, but it's totally different from any other simulators like X-Furuka or Penelope. We do not have any tracking cut. We always try to track particles down to 0 kinetic energy until it completely stops. Of course, if it disappears out of the boundary or it decays, it's not the story. But as long as it persists, we try to track particle to the exact 0 kinetic energy at the stop. Okay. The only cutoff we have is producing secondaries. Because of the infrared divergence, we cannot generate ultra tiny delta rays because it will be immense. Okay. That is the only production threshold. Mihari, I believe, will discuss a lot. So if you want to compare Geant4 result with, for example, Furuka or CNP, you have to be careful because they do have tracking cut. If particle comes down to, let's say, 10 keV, they stop particle there. The difference is, for the case of Geant4, we do one extra effort to make it to simulate the complete stopping point. Okay. So track status. When you do simulation, in each of your track at the end of each step, according to what happened, track has its own state. And if these three states are something Geant4 internally set, while the other three in green is not something Geant4 will set, but you can. Okay? The first is alive, it's healthy, particle is still moving. The stop but alive means it comes down to the zero kinetic energy, but still something to do, like decay at rest. Stop and kill means it's dead or gone. Okay? And this one, you can set this state at the user stepping action if you need. If that means immediately Geant4 forget about that particle. It's typically the use case that if particle comes to the dead shielding block, so that you don't want to care about that particle anymore, you may want to kill it. Okay? Suspend is an interesting option that you may need it for scintillation detector or Cherenkov detector. If you just let the original charged particle go through the entire Cherenkov detector gaseous part, you may end up with huge amount of optical Cherenkov optical rate. So you may want to limit the step short, and once one step is done, you suspend the track, then you continue simulating all the optical photons generated in that part short section, then come back, continue another step, and so on and so forth, to minimize the memory you need. Okay? The postpone to next event makes sense only for the collider detector. If you have a loop path that persists in a tracking volume forever, you may want to postpone this track to the next event. Okay? Now, step status. This is different from track. Okay? For each step point has its own reason why this particular step is made. And if the step status is F, so please note it, step status is both for pre-step point and post-step point. Pre-step point shows why this previous step was made, while after this step, you know why this particular step is made. Okay? If status is world boundary, particle comes to the world boundary, so that particle is going out, you never care. Oh, sorry. No. Then Geant boundary. If this is the case, step is limited by the volume boundary, except for the world. Okay. If physics happens, one of these is chosen, and something else you may not see. Anyway, the important thing actually is quite often asked is, you want to know the very first step in particular volume. Okay? In this case, go to the step, go to the pre-step point, and check if the step status is Geant boundary. That means previous step is limited by the boundary. That means this is the first step in this volume. Okay? If you want to know if this particular step is the last step in volume, do the same but ask to the post-step point. If post-step point is limited by Geant boundary, particle comes to the boundary. Okay? So in sequential mode, we have run manager, event manager, tracking manager, stepping manager. Each has its own run, event, track, step. In multi-threaded mode, I'll discuss it later, but here's master, and each of them are worker thread. Master has its own empty multi-threading run manager, and G4 run that represents the entire run. And each thread has its own local run manager, the local run, and event manager, tracking manager, stepping manager, they are all thread local. Okay. So these ones I talk later. Now, one additional thing you have to do is you have to describe your geometry. Geant4 does not know what you are doing, okay? And you have to pick the physics. Otherwise, Geant4 doesn't know what your intention. And you have to tell what kind of primary event you have. Geant4 doesn't know about it. And once you do these three, Geant4 does its simulation properly, but silently, without any output except the event display. So you have to say what output you need. Okay? For medical people and most of the space people, all they care is dose or energy depositions. It's very simple. We have built-in command scorers, so you can just you don't have to write any single line of C++. We can score. But if you are high energy physicist or some other scientists who really care about detectors, you have to describe sensitive detector. That you have to tell what kind of signal you have to get. Okay. One note when you write your code, unit system, it's always the case of any scientific code. You always have to care about unit. In the case of Geant4, please don't ask what is the default unit. No, because it's hidden even to the developers. I know what it is, but at least it's hidden. Instead, you have to multiply the unit explicitly. So that this case, it's 10 centimeter. Okay? In this case, it's 1 GB. So by doing this, we always convert it to our internal unit. Okay? And also, the readability of the code improves a lot. Okay? And to retrieve the number, retrieve the value, divide by the unit you need. In this case, energy deposition divided by unit MeV, so that you get the energy deposition in unit of MeV. Okay? Don't ask the default unit. Okay? Just divide it by unit you want. Okay? Now, C in, C out. Please do not use std : C in, std : C out. But instead use G4 C out, G4 C error for output, because we buffer it so that you, on a nice GUI, you have output. Otherwise, it goes somewhere, some other window. Okay. And we also have G4 end line. And for input, please use UI command. That I will describe later. File IO is okay. Just for keyboard on terminal. Don't use std : C in, C out. Okay, so pretty much that it. All others are just reading. So let me go to the very last slide. Please. Yes. So this is my very last slide. You have to do 4 things. So 4 things to do Geant4 simulation. First, you have to define the material and geometry. Geant4 doesn't know what you want to do. And all the discussions are in the material and geometry lectures. Okay? And you have to select appropriate physics. Okay? That all goes to the physics lectures. So Mihari and Dennis will introduce you all the physics options we have. Okay? And you have to pick. Then you have to instantiate user action classes if you need. And for sure you need at least one. And that we go through the hands-on. Okay? And you have to define the way to primary particle physics, primary particle generation, you have to describe how you want to start the event. That is primary particle lecture. And then you have to define the way to extract the information you need, or the squaring lectures. Okay? Okay, that's it. Sorry for a bit of overrun.
So now we should have a coffee break, which is good news, right? And I would like to before we go out, reinforce what Makoto has asked. I may ask you in Portuguese to be even more clear. Alguém não conseguiu instalar o Geant4? Pode levantar a mão. Quem não conseguiu instalar o Geant4? Virtual machine. Okay. You had a trouble? Okay, I'll talk to you later then, because the virtual machine was something that I did. So, okay. And I actually I can ask you later. It's a question about that.
Okay.
Okay, so is anyone would like to ask anything to Makoto?
Actually, the one question, one information we have to give is I already run out of the break. What time should we start? In 15 minutes, maybe?
Yeah, around 15.
Okay, so we start at 5 minutes past 11.
Yeah, okay.
Next question.
May I ask?
Yes.
Just a question. The MPI feature is already in Geant4. You cite that you run Geant4 in a supercomputer with MPI.
Yes.
It's already implemented.
Yes, we have some examples